So I believe we're live now. So we'll just give it another minute or two before we get started.
And we do have a poll up right now that asked if you've heard of Iceberg before, or you've had of Iceberg, and do you currently have a data lake as well? So everybody has a data lake, right, Matt?
Yeah. I'll give it another minute. We'll wait until 10:07
Eastern, right?
Yes, Eastern. Yes. We are here in Boston.
Central.
All right, it's 10:07. Let's get going. Welcome everyone. Today we're going to talk about how to build an open data lakehouse using Trino and Apache Iceberg. My name is Matt Fuller. I'm co-founder and VP of product here at Starburst, and I'll let Tom introduce himself.
Tom Nance, Director of Customer Solutions at Starburst, and I am an all-around awesome guy. So I did not put that, but I am actually. So yeah, thanks, Matt.
Absolutely. You'll see a QR code here. If you are able to scan that, it will bring up a Trino and Iceberg cheat sheet for you all to use afterwards. So let me just keep that there for a minute while you get your phones up, and we'll get going. So the way this session is going to work, it's going to be between 35 to 45 minutes. At the beginning, first 10 minutes or so, we're going to give a brief overview of Trino, Apache Iceberg, and then kind of the concept of data lakehouses, really to set the context for what we're going to do in the workshop. And then on the second part of this session, we're going to demonstrate how to use these two technologies as you build the lakehouse architecture. So as I mentioned, here's the agenda: Trino, Iceberg, Trino plus Iceberg. We'll talk about how that helps with a lakehouse, and then we'll go on to the workshop. So first we're going to talk about Trino, or we like to call bring your own data. So I'll talk about high-level Trino. So Trino is a fast distributed SQL query engine designed to query large data sets distributed over one or more heterogeneous data sources. Trino, just for you all who don't know, if you've heard of Presto, renamed to Trino, so it was formerly known as Presto, but today it is known as Trino. And there are really four main use cases we like to think about when it comes to Trino: interactive data analytics, high performance analytics of object storage, centralized data access and federated analytics, in batch ETL processing across disparate systems. So in the first case, interactive data analytics, this is about running SQL queries, whether you're manually entering them through a SQL tool or some sort of visualization tool like Tableau or Power BI or what have you is generating those queries. And those queries are being sent to Trino. We're processing the data as quickly as possible and returning the results, whether it's directly to the user who entered the SQL query or via dashboards and so on. And this is done as quickly as possible. It's a very fast and efficient system. And the next slide, we'll kind of talk a little bit more about how this works. But for now, think of it as a SQL processing engine. If we move here to the right, high performance analytics of object storage. So this is really what Trino was built originally for the ground up from, the ability to run SQL analytics on cloud object storage or even data that you still have in HDFS or Hive style tables. And Trino's scale and performance allow for analytics that were either previously impossible or would just take many, many hours to complete and therefore infeasible to run. And then one of the really unique things about Trino is, while it was built from the ground up for SQL analytics on data lakes, on cloud object storage, and so on, it also has this notion of a connector model, being able to connect into data sources that are outside of the lake. So we like to think of this as helping you kind of augment your data lake data of other data sources in and around the lake. So for example, being able to query from a MySQL or a Postgres system directly to do data discovery, join that into your data lake data. So not always having to replicate the data to the lake. So really increasing that fast time to insight. So it can really be that single point of access to your data. And as I mentioned, Postgres and MySQL, but actually one of the nice things is it actually can query data sources that don't look relational. So if you want to query Elastic or MongoDB, their connector model makes it appear as if a table in Trino. And then lastly here, we're talking about using SQL to do analytics on the consumption side. But a lot of people are using Trino as well on the kind of the data engineering side to do batch ETL processing. So think data lands into your data lake, say it's an S3 or Google Cloud Storage or Azure Data Lake Storage, and you need to do some more processing and transformations in order to make that data consumer ready. People are using Trino and SQL to do that processing. These workloads are typically very heavy lifting workloads as you're processing it. Say some JSON data from your application landed in the lake and you want to process it to flatten it out to something more relational. You're reading that and then you're writing it back. And Trino can be run in a very performant and fault tolerant way that can guarantee that those queries complete. And you can rely on the system, so then the downstream systems can start consuming from those data that are prepared. Kind of high level, this is what I was describing here. Trino is the engine. It provides a SQL interface to a variety of tools, so the BI tools, as I mentioned, but also developer tools like Python and DBT and so on. And I forgot to mention DBT is also commonly used with Trino. DBT being used to kind of model your data and make the DBT models. It's issuing SQL queries to Trino, and then we're processing that data on the lake. And on the bottom half here, these are the types of data sources that Trino can query from. So very popular to use Trino to query data from the lake, whether it's in the AWS, Azure, or Google stores, but also, legacy Hadoop systems or and then on top of those, kind of the more modern table formats like Iceberg and Delta Lake, for example. We'll talk about Iceberg in just a bit. And who uses Trino? If you go to trino.io, there's a list of companies that have self-selected and put their logo on the site of people who are using Trino at scale. And it's really being used a lot by a lot of companies across industry. And this is just really a small sample of the type of customers that are using Trino today. And so high level, how does Trino work? So I talked about why it's fast. I'm going to talk about, just go into a little bit more. We're going to double click into why it's fast and how it performs. So Trino is a distributed system. So what does that mean? There's really kind of two concepts here. There's a coordinator and any number of workers, and that makes up a Trino cluster that does the data processing. So you can think of the coordinator node as sort of the brain of the system. This is where the SQL query comes in, whether it's a user submitted query or one from a tool, like a BI tool or a SQL developer tool. And this coordinator is going to parse the SQL. It's going to plan and optimize it. It's going to get that metadata from the data sources. So, whether it's from one of the relational sources we can connect to, or if it's going to in the data lake, it's getting metadata where that may store it in a metastore. And it's going to do some scheduling. And then finally, it's going to put the plan on the worker nodes. And this, you can think of the workers as the muscle. The coordinator is the brain. The workers are really the muscle. And that's where the heavy lifting is doing. That's where all the processing doing. And it's a completely distributed system. So workers are getting a piece of the data. It's all happening in parallel. And eventually the results are returned to the user who issued the query. So next, I'm going to hand it over to Tom for Apache Iceberg. I talked about how Trino is bring your own data, and Iceberg's about bring your own compute. So here you go, Tom.
Great, thanks, Matt. So what is Iceberg? If you look back at about 10 years ago when Hadoop was just gaining traction and very popular, a lot of data was stored on just gzip files and JSON or CSV or something like that. And then we had a columnar formats that were created. So Parquet or Orc was a columnar-based format for a file that really increased the performance of doing analytical type queries. But from there, you still couldn't do updates and inserts, and there was a lot of challenges still around this massive amount of files that you needed to read. So the idea of like a central table storage kind of became popular, where you have the independent, so you have basic data that's independent of compute as well. And then you have lots of file partition because you had so much data that you would partition usually by day or something like that. And then you actually have schema evolution that we had to worry about. So if you did have a table or a column that was added, which happened a lot, that was also a challenge to handle in just a typical Hive-based environment. And also is just the multi-engine support. So how do you have, different kind of engines that are supporting the different kind of file formats that are out there? So next slide. So the Hive connector, I talked about this a minute ago. It really relies upon something called the Hive metastore to store all the metadata about tables and structures. And that's usually what happens is that becomes the bottleneck in a big data system is if you ever use like a Hive metastore or even possibly Glue on AWS, you're storing a lot of information. So every time you run a query, you have to ask that metastore for a lot of information, just not the information about the table, but a lot of statistics. So that was usually a bottleneck in a lot of people that we've dealt with before. And also the partitioning in Hive, it has to be based upon column names within a table. So if you have a table and you want to partition it, the last columns in the table need to be the partition columns. And so you would have to teach your end users to make sure they write the where clauses and filters based upon those partitions, those columns. Otherwise, you're going to do these full massive scans over these, terabyte, possibly petabyte type tables. And also it wasn't optimized for storage. So for object store like S3. And when you're looking, when it first created, it was great for HDFS. But when you start moving into the object world, the way it was partitioned out was a year equals whatever, month equals whatever, day equals whatever, like my example in the lower left. That's not very good for an object store. They just want basically an object store. You want a key value pair. And so something like a table format or storing that data differently is a lot more optimal. And also the object stores listing is very costly. So every time you had to go query a table, you had to go to like, let's say S3 on if you're on AWS or Azure, you'd have to ask for that listing of files. And that can get very costly as well. So every time you're querying, you're going and looking for these massive listing of files from the cloud provider. And also scaling a Hive metastore is very difficult too. And also the relational databases that are back in Hive metastores, those also turn into a big bottleneck as well. So we had something that worked out, initially very well, but as we grew more and more larger tables, more partitions, this just wasn't working out very well, and especially with the move to the cloud. So next slide. So what is Iceberg? It was created by Ryan Blue and Daniel Weeks at Netflix. It was really, it was created to solve the problems that I just talked about before. So data modification, how do you actually modify data in a data lake? How do you handle schema evolution as well? And so what they did is they made sure that you didn't have to use some kind of special file format. You still can support ORC and Parquet and Avro, but really think of this as just a layer of metadata that sits over the top and it describes what's going on with your table. It's kind of like a database. Database has a transaction log, same thing with Iceberg, except for it's just stored with the table information, let's say on S3. And so what's really nice is you have a lot of different engines now that are supporting Iceberg. So you can create a table in one engine that you can see in the upper right, and you can also read that with another engine. And this is something that we've really never seen before, where you have the ability to do update, inserts, partitioning, higher performance, all on top of your object store in any of your clouds and on-prem as well. And then have these different engines that you can plug and play into it. So it really gives you like a real open architecture when it comes to a lakehouse, which we'll cover next. So what are the features and advantages of Iceberg? In the upper left, you have the concept of snapshots, which is very similar to a database where you can roll back to certain snapshots. So anytime you change a table, a new snapshot is created. And then that snapshot basically has a listing of all the files that belong to that table at that given time. So that allows you to do something like time travel. So I want to go back to the previous update of this table and see what the actual data was. And also it reduces the metastore reliance. So when you look at something like Glue, the only thing you have stored in Glue is just a pointer to the latest snapshot. That's it. So that brings that lowers all the concurrency that you have when you're hitting a Hive metastore. And also when it comes to concurrency too, there's something called optimistic concurrency. So when there's certain types of writes that you can do all day long to an Iceberg table, you can insert all day long because they're not, you're not conflicting. So when it comes to updates, then you want to make sure, so each of the engines have this built in to where if two people are updating the table at the same time, someone has to win that. But when it comes to like inserts and that type of stuff, there's never any kind of blocks. And also schema evolution with Iceberg, it tracks all the columns by ID. So you can easily add and remove columns. It does also support of nested evolution as well. So a lot of the the features we had in databases have now finally come to a data lake. And there's also something that Iceberg calls hidden partitioning. But if you've used partitioning in a regular database before, it's just like that. It's just taking a table and then using that column to do the partitioning on. And then all the work clauses are basically based upon that table, that column anyway. So really it allows you to do, like I have an example here. I was using regular time series queries, which is usually what you are partitioning by, especially in a big data like event, IoT type or sales type fact tables. You're almost always partitioning by some kind of a timestamp. And so instead of breaking that out like you would have to do in Hive, you could just say in this example I have here, I want to partition by year. And you can modify that later, which is really nice about Iceberg. You can say, okay, well, I actually under partition this, so I want it to do year and month. So you can modify that at any time, which you could definitely not do in the Hive connector. So next, and then so in addition, there's one big performance improvement that I like about Iceberg is because you're not doing this constant file listing from the cloud provider. When you have a snapshot, it has the listing of all the files that belong to that table. So when you want to read, you're just reading that snapshot, and then you're going to go read those files that belong to that table. So that takes the Hive metastore out of the performance bottleneck. That also takes the cloud provider out as well. So all you're doing is you know exactly which files you need to go read, and you go read them. There's also statistics in each of those files based upon those different columns. So based upon your work laws or your query, you may not have to read all these files. And that could be a huge performance benefit, especially if the data is sorted by one or more columns that you have that you're filtering by. And also is the big one is allowing DML. So being able to update, inserts, and deletes on that data, especially for like GDPR, which really hit the Hadoop world hard because everybody had all this data stored in Hadoop, and to be able to do point or row-based type updates or deletes was basically impossible. So that really hurt a lot, and that's why something like a table format like Iceberg really helps with that. And also there's optimize commands. So since you are a snapshot transaction-based type of architecture, you're able to run an optimize, which means if you're pulling in a lot of smaller files that are really bad on performance, you can run an optimize command that'll take a lot of those small files and make them into larger files. And it does that all while having read level consistency. So it doesn't interrupt the readers of that table. It just works on those files, makes them larger, and then creates a new snapshot when it's done. So it doesn't affect any kind of the read. So it's not like you have to have a downtime or anything like that. And also I kind of talked about this before with sorted tables. So if you do have, let's say ID or region ID or something, or your query patterns for a certain table are always by one or two columns, then you would want to sort those tables by that column. And so as you're writing data, that data is sorted per each file based upon that column. So when the optimizer, when you're running a query in any of these engines, it's going to look the file metadata that I covered before and allow you to skip whole files. So you could have 10,000 files in a table, and you may only need to read 5 of those files or 10 of those files. So you can see huge amount of performance benefit versus just regularly reading all those 10,000 files in parallel and trying to filter that out. And then lastly is the vacuum command. So vacuum is basically all those old snapshots, all those old files that you leave run. You just want to vacuum and clean up the old snapshots because you don't want to have a bunch of data laying around that you're just paying for that you're not going to use. So next one. Next, we'll talk about the architecture of Iceberg. It's consistent of basically the metastore that I was talking about. And then every snapshot is basically called a metadata file. And so every time I do an insert or an update or a delete or a merge into an Iceberg table, I create a new snapshot file. And that snapshot file, it points to manifest list files and data files. And what that does, it kind of creates like, it's an organized spider web, as I call it, but it allows you to do a lot of reusability. So let's say if I'm constantly inserting, all I'm doing is creating this new metadata files, and I'm just pointing to those existing manifest lists and any new manifest lists. So as you can see, an initial write to a table is actually pretty small because you're only writing one metadata file and then another manifest list, and then you're just reusing. So you can see in the upper right, there's that second metadata file that points to snapshot 0 and snapshot 1. So it's just there's a lot of reusability in Iceberg, and that makes it really fast. And then it also makes it so you can do time travel very, very easily because you have that whole hierarchy built underneath you. And again, one thing I wanted to cover was it does cover ARC, Parquet, and Avro. So your files could just be in an open format, and that hasn't changed. Again, when you're talking Iceberg, this is what you're looking at right here. That metadata layer is really makes up Iceberg. It's just this metadata layer that sits over the top of your tables. So if you combine these two together, it's kind of like a perfect storm. It's something I prefer, personally was waiting for a long time. I absolutely love Trino. I love what the engine. I love bringing your own data. But to me, I came from 20 something years of doing data warehousing and ETL, and really I needed ACID transactions. I needed to be able to update data, dimensional type data, reference type data. And it was very difficult how we had to do this in the old days in Hadoop. Was you have to just basically rewrite whole tables to do any kind of updates. And it was just, I felt like I was going back in my career. So I was very excited when Iceberg came out, because it allowed you to do, ACID transactions. So if you look at these two different kind of columns here is, my world was the data warehouse world. And then I kind of got into the data lake world on the right-hand side. And I was used to ACID transactions, fine grained access control, the data quality, be able to have more structured type tables that are in a data warehouse. And then the high performance concurrency, that's really what, a lot of these EDWs brought you, is really, 1 millisecond type queries. And then really best for, business intelligence use cases. I think a lot of people kind of got into Hadoop and they backed away or ran away from it, I guess I should say. And they just thought it was a data science, a Java type machine learning type environment. So we still run into that day. We still run into a lot of people that have lakes, they land data there, but they put it somewhere else just because they don't trust the data, or they just don't know about this technology that could sit right on top of a data lake. So you look on the right-hand side, the data lakes brought us stuff that we were stuck with in the EDW world, like the separation of compute and storage. Every single data warehouse vendor that I worked with had all the storage that were basically attached to the node. So that was the big thing with Hadoop, is bringing the processing to the data, but then you're kind of stuck. So now you have everything's together. So if you wanted to add another box, you have another bunch of CPU and then a bunch of storage. Even if you just needed more CPU, or if you just needed storage, there was no way to do that. So what was nice about, especially Presto at the time, was this idea of, I'm just bringing compute to the storage. And that was new, even in the Hadoop world. That wasn't really, a lot of times we would install Presto and Trino in its own separate servers. And, the Hadoop world's like, no, everything has to sit on the entire Hadoop cluster. And that's not how we operated. We just would attach to the storage. We would read the storage, and it didn't matter if it's HDFS or if it was MySQL or Postgres, it didn't matter. So bringing that separation was really big. And then really large scale. So adding hundreds of nodes, that was never seen in the data warehouse world. If it did, you'd have to have the treasury fund you. This is impossible to do that. So really low, commodity type servers. That's where, Google was very popular bringing it. Just these off the shelf generic boxes that they would fill these data centers up with that were dirt cheap to do. And so then open formats, that was another big one. Like everything with Oracle and everything else was proprietary formats. So now we have Parquet and Orc coming along. That was a columnar format that broke open the whole analytics industry, where now you have something that everybody can share. Anybody can read a Parquet or Orc file these days. And that's something that we couldn't do in the data warehouse world. And then handle structured and unstructured. I'm not a big fan of the word unstructured, because it means, like, to me, data always has structure. It may change as you're going through, but really, I mean, that's something that was brought, it was kind of being added to the EDW world, but really JSON and modified JSON. For every time you have a new file come in, you could have a different structure to it. And so being able to handle that in the Hadoop world was big. And then open source options, like I talked about, there's not just, then EDW, you had a lot of different kind of open source projects out there that you can work on your Parquet and Orc files with. So you combine these two together, and then something that we call the Lakehouse, or is kind of known in the industry now, is combining both of these together. And I think that's where we're at right now. Is we like to call it have your cake and eat it too, because it gives you all the benefits of a data warehouse and then all the benefits of a data lake as well. So if we this is similar to probably something you've seen before, but this is the stack, we like to call it. So you have the object store on the bottom, you have your different open file formats, you have a table format like Iceberg, and then you have compute engines. So if you add these all together, especially, the middle two part are open source. So they're not owned by anybody. File formats, the one was, Orc was started by Hortonworks, Parquet by Cloudera, but those are completely open sourced formats. The same thing with Iceberg. Those aren't owned by any kind of company. And then we have Trino, which is a completely open source compute engine. There's a bunch of other, like we showed earlier in that diagram, there's a bunch of other compute engines that support this exact stack as well. And so this is, completely open Lakehouse, which is really what we like. You shouldn't have your data locked into someone, you may, your vendor may use S3, but it's not even in your account. It's locked away somewhere else. And every time you want to touch that data, you get charged for it. You can't choose any of these really cool other compute engines that are available. So this is what we call the complete open Lakehouse stack. And then next, we're going to get into our workshop.
Yeah, absolutely. And before we get into the workshop, I just want to mention that we still have the poll open. So if you want to go to the poll, it's have you heard of Iceberg, and do you currently have a data lake? And actually, it's funny. There's a slight typo on the question. It says head of Iceberg, so just remind me of lettuce, but it's supposed to be heard of Iceberg.
That's called an overpriced salad at a steakhouse.
Yeah. Let's see here. Okay, so what we're going to do for the workshop is we're going to use our product here called Galaxy from Starburst, and then we're also going to use a product called Tabular. So here at Starburst, we're the commercial offering based on the open source project Trino. It really is the easiest way to get up and running with Trino, as well as providing a wide variety of other features such as security and so on. We're not going to get into everything today, but it's the simplest way to get going with Trino. Same with Tabular. Tabular is the simplest way to get going with Iceberg. So we're gonna show how to build a lakehouse using these two products today. Both are using Trino and Iceberg, but it's really the fastest way to do it. We're going to do it all through within a web browser today. So here I am with Galaxy, and what I'm first going to do is kind of introduce you to the concept of clusters. So you're able to create a cluster. A cluster is really a Trino cluster that you're submitting queries to, and then I'm going to show how we can attach Tabular to the Trino cluster. Remember, we're talking about how Trinos bring your own data and Tabulars bring your own compute. So we're going to configure a tabular catalog and attach it to the compute, which is the Trino cluster. So what we can do here is when you're in Galaxy, you click on catalogs here, you create catalog. And there's a number of tiles, the type of data sources you want to connect to. We've talked about S3, Azure Data Lake Storage, and Google Cloud Storage, but Tabular is a managed Iceberg service on top of S3. So what I'm going to do is I am going to fill out a few basic fields here, Tabular demo, and what I'm going to do here is I'm going to I'll show you Tabular in just a second, Fuller Tabular warehouse. And then I'm going to go into Tabular. This is Tabular, and we already have some example data being managed here in Tabular. This is in your own S3 bucket, but Tabular is managing the access to the Iceberg files, as well. It does a variety of other things such as compaction of the data and data retention and so on and so forth. So the only thing we have to do here is we just have to give Galaxy access to Tabular. So they have a feature here to create a credential. I am going to call this Tabular demo Fuller, and I click create. I'm just going to copy this. I'm going to go back over here into Galaxy and paste it in. You can see it's just a bunch of string, and then we're going to click test connection. And hooray, I can now add this catalog to a cluster. So I'm going to connect catalog. I'm just going to skip this, and I'm going to skip this. And now it was added. Now, for the purposes of time today, I already have a cluster running connected to Tabular, but I just wanted to show you how to create it. But if we were to create a new cluster, we would just do, I'll just call this demo. Well, we already have one called Tabular, call it Tabular 2. And then we would choose the catalog that we just created, as well as the region of AWS we want to deploy to, and then we click create cluster here. But I'm going to go right into it here. So first thing I'm going to do is in my worksheet here, I'm connected to the cluster I already have running, Tabular in my schema Fuller. So I just want to do a quick query to make sure this is all good before we get going. Perfect. So I'm going to walk you through our worksheet here, which has some SQL to show you how to create this Lakehouse. So the first thing I'm going to do is I'm just going to create a new schema called Fuller 2 because I already have this created as Fuller 1. And then I'm going to just use Fuller 2. There we go. So the first thing I'm going to do is I'm going to create a table. And so these are column names with the types and comments. It's best practice to put kind of comments of, what this is. And then, as Tom was mentioning on his part on Iceberg, there's the concept of partitioning. So there's pickup time, which I believe is a timestamp, but we're extracting out the month and we're partitioning on that. So let's create this table. And then we can see that we create it by running the describe command here. So let me get some more screen real estate here. There we go. So you can see that we now are showing column names, types, comments, and so on. So the first thing we're going to do is we want to insert some data. So what we're going to do is we're going to query from an examples table that's here in Tabular. There's an examples table. New York taxi yellow, I believe. If you go back here, you can see that schema we created when I ran Fuller 2. You can see it's now here in Tabular. But there's no tables in here yet, or rather, there's no data in that table yet. So what we're going to do is we're going to select from the examples table, and we're going to put February from 2019 into there by using an insert select statement. This is a fair amount of data, so it will take a few seconds here. So about 30 seconds, we loaded that data into the table. First thing I want to do here, let me run a query to show that there's now data in this table. Perfect. However, what you'll see is, remember that we said, where month equals 2019-02. What's typical in the data world is your data is not always clean, and you can see that some of these were 2038, which hasn't even existed yet. So it did load in data because the data wasn't clean. However, because of partitioning, you'll see that Iceberg automatically partitioned the data so that all the February of 2019 data is in the same partition. So even though we loaded some incorrect data in, it was still partitioned correctly. And we can run a query here. So the next thing we want to do is we want to load more data into the table, and we can do this using the merge syntax. This is how you can start to create data pipelines. I'm going to hand it over to you, Tom, to kind of talk us through this, and I can run the queries as you talk through it.
Sure, especially when you're pulling from you have a source table that you're landing data to, and you want to do inserts or updates into a target table, and that's where the merge statement's really going to come into play here. And this little segment right here that we run, we're going to put this actually into a merge statement, but this is actually deduplicating the rows. We want to make sure that we don't, especially in the source system, may have duplicate rows. So if we just blindly insert rows into a target table, we're going to have duplicate rows. So what we're doing here with this SQL statement is basically deduplicating the rows. So when Matt runs that, which I think you already ran that, that's just going to go through, and I don't know if you ran that or not yet, but this is just going to say, okay, these are the different, we want to make sure that what we get out of this statement is no duplicate rows at all. So this will deduplicate for us. Now, if we go down into the merge statement, we're going to add that and make sure that the data that we're dealing with has been deduplicated, basically in line. And then now this merge statement is going to just do an insert or update into, actually just going to do an insert basically into the target table here.
Right, exactly. And you're just looking closer at this, it's the reason why it's deduplicating is we're using the row number function, and then we have the predicate here where it's row number equal to 1. So if there were duplicates, it only picked that one.
So typical like ELT type of work is making sure you have data, the correct data quality that you're going to put into your data lake. And then from here, we're going to run the merge statement. So this is just going to look at all the rows in this source table that has been deduplicated, and then look to see if it's matched in the target table. If not, then it's going to go ahead and run an insert. So the first time obviously is going to take a little bit because we're going to do the entire month. That's 7 million, I think it was, of rows, and we're making sure that those don't already exist in the target table. So that took about 30 seconds there. So it's 7.8 million rows that were inserted into the target table.
Yep. And this was from the month of March, whereas before it was February. The other thing to point out is these merge statements are idempotent. So if you were to run it again, that's the whole point behind when not matched. So it's only adding new rows. So you're getting that clean data.
Right. Now what we can do is add a little bit of actually, I think that's the next one we're going to run, right?
I think right now I'm loading in April, but why don't you talk through as you start to add more and more months, it starts to take longer.
Correct. Yeah, because what we're doing is we're going over the entire target table. So we're making sure the entire target table is going to do an insert, and then we're looking at the entire source table as well. So as we're going through day to day or month to month, whenever you're going to run this, we want to make sure that we're only looking at data that we care about that we've already gone through. So all we're doing is adding some WAR clauses. You can see down in line 181 and 182 is we're just adjusting that. So whatever, scheduling tool or whatever you're doing, you're just going to be adjusting the day. So this will really narrow down the data that we have to deal with. So when we run this, it'll just have to worry about 8/1, so this is going to be the months of July 2019, and that's it for that. So when you run this, as you're going through, you're growing and growing, as a year or two, it's going to take a lot more because there's a lot more data you're going through. So when you run this a little bit, so this is just a different day that we ran here. So that's a little bit different for July is 6 million rows. So right around the same.
And I guess just to kind of provide context where we are, remember at the beginning of the session today, I was presenting different Trino use cases. This is really on the ETL side of the use cases. We're doing these heavy lifting queries as we prepare the data for consumption. But just wanted to, is this the query history? Oh, refresh results. I just wanted to show.
Yep. I think what happens is we have other people running stuff on here as well, which doesn't help. So,
okay.
Yeah, that's probably what's
okay. There we are. There we are. Okay, great. Yeah, what I wanted to show was the improvement we did to that merge statement. So if we go to advanced here, we're seeing, we're reading, 22 million rows, number of bytes read, peak memory, and so on. But let's keep at 22 million rows. When we go back, click here. You see that the rows read is significantly less because we had put that predicate on. So we're just reading less data. So that's one of those optimizations we can do as you're preparing your data.
Yep. It makes a ton of difference in performance, definitely.
Yeah. Do you want to talk through this update statement?
Sure. Yeah. The next thing we discovered that is the data. The trip distance is not rounded up. So it's very difficult to run reports. You have to start having users run casts on data, and that's usually what we'd have to do in the Hadoop world. And now with Iceberg, we can just update data directly in the target system. So what we're doing here in this update statement is we're rounding that trip distance up to the nearest, I think 1 mile, I think it is, based upon this date. So if Matt runs this, it's just going to go through and use some Iceberg magic underneath the covers. Right on top of S3 is where our demo environment is. So it updated that. And so now that we just did a small amount of data, we didn't do all the data just for this demo. So now if you run the next query down, is you'll see that now the trip distance is to the nearest mile. So instead of having decimal points in there, this is mostly what the end users want. It's just they wanted it rounded up.
Yeah. Do you know what I forgot to do, Tom, though? Is I forgot to show what the data originally looked like before we rounded it.
So,
but
yeah, so
we could go back in time though.
Yeah, I didn't. Yeah, just like the DeLorean. So
yeah, exactly. So let's see. So when there's a kind of a special table called history. And remember how Tom was talking about in the architecture, you have all these metadata files. We're actually able to keep versions of the data. We're calling them snapshots. So this is the latest one here. Well, let's take this one for example. And let's run that same query again. But instead, there's this special closet here for version as of, and I'm going to put in that value I just pasted in. And you can see that these are the original data before we rounded it, before, you know, the command Tom was talking about before we rounded it up.
And to be clear, like there's nothing magic we're doing here. So this data is sitting on S3. There's different snapshots in S3. You could have done the same thing, let's say with Spark that supports Iceberg as well. So this isn't something like Starburst or Trino is doing magically. This is just Iceberg. This is what's so cool about it.
Yeah. Yeah. And it really gives you that functionality you're used to with databases and data warehouses, but doing this on the data lake, you really are getting the best of both worlds, the cost and efficiency and scalability of the lake with all this you know, traditional database functionality. So let's do this one. So we showed an update. Let's show how you could delete data. In this particular example, we're gonna delete where pickup location ID is for. You know, you could think of other use cases. Tom mentioned GDPR earlier.
Yep.
Someone wants their information removed from your system. Previously, literally impossible or very expensive to do in, you know, traditional Hadoop or traditional data lakes, but with Trino and Iceberg, you're able to do this.
Like partial loads. That was the other thing that we always had a tough time in Hadoop. If you did you know, partially loaded data, it's like, what did you do? And so you could actually go down to a snapshot and delete by the data that you added that per the snapshot. So something you can never do back in the Hadoop world or Hive connector.
Yeah. And so now when I run the count on this table where pickup ID location equals 4, we're getting a value of 0, which is not surprising. We just deleted the data. But you know, we can go back in time. I just need to run this history so I can get the snapshot ID here. And so if we run that query again, you know, we can see, you know, how many. So it used to be 13,520 of those rows were pickup location 4 that we, you know, had deleted. So that really, you know, concludes, you know, how you can, you know, build a Lakehouse architecture using Trino and Iceberg. You know, in summary, you know, we talked about Trino, it being a compute engine to query data where it lives, in particular on your data lakes that are in cloud, you know, object storage like S3. And then we talked about Iceberg, which provides that table format over open formats like Parquet and ORC and so on, and combining these two technologies to give you that best of both worlds, the database data warehouse functionality with the scalability, performance, and efficiencies of the lakes. And then we demonstrated this using Starburst Galaxy, which is a SaaS offering for running Trino clusters, and Tabular, which is a SaaS offering for managing Iceberg as a service. And thank you for coming. I see that there is one question here in the chat, and the question's around how Trino can support state and municipal authorities. You know, is it, you know, is this something you can do with Trino for the data lake? And you know, I would say is Trino can be applied horizontally across many industries. So if you have data that you want to analyze, you can build a Lakehouse architecture and absolutely use Trino for that. In fact, we have here at Starburst, we have many customers in kind of the health services space with a Lakehouse architecture and using us to query that.
Yep. And I posted and hopefully I put it in the right spot. I put it in the webinar chat, just a blog post that I wrote for kind of what you're talking about, just landing data in this blog post. I land data in JSON files. And then from there, I insert them very close to what Matt was showing us, is inserted that into an Iceberg table. And then from there, I built reporting structures all on top of S3 in a very, very low cost way of doing analytics. That traditionally you'd have to go into like a cloud data warehouse or something like that. So I put that link in the chat there. And
Um,
Shamel, I think I pronounced that right. That was from Shamel. Hopefully I pronounced
Yep.
that right. So
absolutely. Cool. Tom, anything else, or are we ready to?
that's it. One thing to note about with Starburst Galaxy, you can just go to starburst.io and sign up for Galaxy. We have a free cluster on there you can play around with. We have a bunch of data sets. You can play around with Iceberg. You can open up your own AWS account for free and throw some data on there and play around with it. If you have any questions, just email, contact us. You can contact us through Starburst Galaxy or just go right on the website. So
Yeah. Yeah, it's a good point. In addition to the free clusters, we also have higher paid tier clusters that can kind of get you more performance. But if you sign up, we actually provide $500 in free credits. So you always have the free tier cluster, but if you want to add a little bit more horsepower, remember when I was talking about the Trino clusters earlier, the more workers you add, the more performance you get. We also have those available, but you can use the 500 free credits towards that if you want to try that out as well. So free tier, we always have that, plus 500 credit for the paid options as well. So thank you all for coming to our session. Really appreciate it. And as Tom mentioned, please reach out if you have any questions. Bye now.
thank you.